Harnessing Nonlinearity Part 2 Rotation Number, Twist, and Detuning. In our studies of single particle and collective dynamics, we often rely heavily on sophisticated simulations to get precise quantitative results. Who knows, maybe one day we'll have AI handling every calculation for us, right down to the smallest detail. But we are not there yet. And before we trust any detailed prediction, we need a solid, qualitative grasp on the overall system behavior. And this is exactly the goal of the second part, to develop a clear, qualitative understanding of the fundamental concept of detuning. As always, before we dive in, let's first revisit a few important definitions. If a system is integrable, we often switch from the traditional coordinates and momenta to a set of action angle variables, where remember the prime to denotes the new value after one iteration of the map. J is the action variable, which remains constant, and theta is its conjugate angle, which advances each turn according to amplitude-dependent rotation number, nu of J, the so-called nonlinear Betatron tune. If a system is chaotic, we don't give up. And for quasi or nearly integrable trajectories, most analytical or semi-analytical techniques still seek such variables. The rotation number, which in general is defined as a limit, when that limit exists, represents the average angular advance per iteration, normalized to 2 pi. Often, the rotation number is expanded as a power series in the action, where its derivative with respect to J is known as the twist. The coefficients in this expansion are called twist coefficients, with tau 0 referred to as the detuning. This detuning is a fundamental intrinsic parameter that captures the leading order nonlinear effect in the immediate vicinity of the equilibrium orbit. Because it plays a crucial role in understanding single particle stability on nonlinear resonances, it provides valuable guidance for setting up resonant extraction and, at the same time, allows estimates of the tune spread in a beam, which in turn helps determine thresholds for collective instabilities. Next, recall that the linearized dynamics near a fixed point, aka equilibrium orbit, is described by the Jacobian matrix of the transformation. In our usual phase space variables, the physical coordinate q and its conjugate momentum p, the Jacobian matrix is composed of the first-order partial derivatives of the map. The symplecticity requires that the determinant of Jacobian matrix equals to unity, and for stable oscillations, the absolute value of the trace A must be less than 2. Evaluating the Jacobian at the origin, p equal q equals 0, gives us the bare Betatron tune directly. In contrast, determining the detuning, the first twist coefficient tau 0, is a considerably more tedious task. I often found myself stuck trying to answer what I consider very basic questions about detuning without restoring immediately to rigorous calculations. Calculations that, while correct, sometimes leave you with an analytical result but no real intuition. Never liked shut up and calculate approach, to be honest. So to show what I mean, I invite you to test your own understanding. If you're a student, try this on your supervisor. And if you're a mentor who knows the answers, make sure your students do too. Let's keep it simple. Imagine a model accelerator lattice with only one degree of freedom, say the horizontal plane. The entire machine is linear, except for a single thin nonlinear lens. For our discussion, let's stick to the two most common nonlinear magnets, the sextupole and the octupole. Now, in this simplified setting, let's attempt to answer the following not-so-simple questions. What is the sign of nonlinear detuning for a sextupole or octupole magnet? Does the detuning depend on the bare Betatron tune nu0? What is so special about the irrational Betatron tune of approximately 0.29? The one that gives a Jacobian trace equal to -1/2. Why does a sextupole drive a quarter integer resonance, while an octupole drives a third integer resonance? And are the third and quarter integer resonances stable for these magnets? If so, why? Pause for a moment and see what you really know. In the rest of this tutorial, we will aim to build a qualitative picture, or at least point in the right direction. But here is a sneak peek at the answers. First, for a sextupole magnet, the sign of the detuning depends on the bare tune, whereas for focusing and defocusing octupoles, the sign is strictly positive or negative respectively. Second, and somewhat surprisingly, for the octupole magnet, not only the sign but also the actual value of the detuning remains constant across the entire range of tunes. Next, the special tune of approximately 0.29 corresponds to a twistless bifurcation, relevant only to the sextupole magnet and indicating the appearance of an orbit where the twist vanishes. Finally, thin sextupoles and octupoles are not simple, pure quadratic or cubic nonlinearities, as they might initially appear. Rather, each comprises an infinite series of elementary components, each resonating with different rational tunes. Among these resonances, only the third integer resonance of the sextupole is genuinely unstable, or more precisely, singular, with the first twist coefficient diverging to infinity. If you don't feel you have a complete intuitive picture, that's normal. These answers usually raise more questions. Just in case you'd like to see the analytical expressions and how they depend on the Betatron tune nu0, here they are, where beta is the value of the beta function at the location of the thin lens, and k is the integrated strength of the nonlinear magnet. On the next slide, the yellow curve, labeled as x2, shows the detuning for a thin sextupole magnet as a function of the bare Betatron tune. We see that the detuning is negative everywhere except in the interval from that special value of nu0, approximately equal to 0.29, up to the third integer resonance, where the first twist coefficient becomes singular. To develop a clear qualitative picture, let's take a quick detour back into continuous time integrable Hamiltonian dynamics and see how it's done there. Instead of a thin element, now consider an infinitely long nonlinearity. In other words, one that is uniformly distributed around the entire machine circumference. The resulting paraxial motion is then described by the standard Hamiltonian h equal p squared over 2m plus potential energy. If the potential energy has a minimum at the origin, its Taylor expansion begins with quadratic term. The bare oscillation frequency, the analog of our bare Betatron tune, then depends only on the second derivative of the potential, or equivalently the first derivative of the restoring force F, each evaluated at the origin. Further, by an appropriate choice of time units, we can always set the bare frequency omega 0 to 1. This leaves us with only two parameters, B and C. Note, however, that this simplification is not possible for mappings, since the linear Betatron tune carries important information about the rate at which our thin perturbation is applied. The general result shows that the detuning depends only on the next two derivatives and is described by a relatively simple equation. This equation offers several valuable qualitative insights. First, the effects of quadratic and cubic nonlinearities are additive. However, they contribute qualitatively differently as B appears squared. A distributed sextupole and defocusing octupole have the same effect on the sign of the detuning, while a focusing octupole acts opposite to the sextupole. So when two components are mixed together, the overall outcome depends on their relative strength. Therefore, we see that distributed sextupole and octupole are the two fundamental components of general nonlinearities that allow atypical expansion, meaning at least one of the coefficients B or C is non-zero. These important integrable systems admit very compact and elegant solutions, expressed in terms of Jacobi elliptic sine and cosine functions. Such functions naturally extend the zeroth order, in other words linear, approximation of harmonic oscillations described by standard trigonometric functions. Moreover, not only the detuning and solutions to the equations of motion, but also the full dependencies of the frequency on the action variable j can be found analytically. The resulting behavior is relatively simple and shown in the figure below. For the sextupole, orange curve, and defocusing octupole, red curve, the frequency decreases monotonically to 0, while for the focusing octupole, curve in blue, it increases monotonically to infinity. Now we turn to the main result. Just as the distributed sextupole and octupole act as the two basic components of nonlinearity in the continuous case, there are two special integrable systems for the thin lens case that serve exactly the same role, namely the canonical Macmillan sextupole and octupole mappings. While this tutorial is meant as a teaser for the full articles listed here and at the end, we'll briefly reveal the key results by giving a qualitative comparison to the continuous time dynamics and leaving the lengthy formulas outside this short presentation. First and foremost, Macmillan multiple mappings are integrable and possesses an invariant of motion k that, just like the Hamiltonian in the distributed lens case, includes only quadratic and cubic terms in the dynamical variables for the sextupole and quadratic and quartic terms for the octupole. Next, not only the invariant but also the solutions to the equation of motion are once again given by the Jacobi elliptic sine and cosine functions for the octupole, and by a slightly more complicated function involving sine squared for the sextupole map. What is really different is the magnet's kick functions. While in the Hamiltonian systems both the force and the potential were polynomials, the force functions for Macmillan multiples are given by rational functions whose polynomial degrees are no greater than 2. Looking at the power series expansion of the kick for the Macmillan sextupole, we see that this basic nonlinearity includes not only the linear term proportional to q and the quadratic term proportional to q squared, which corresponds to a conventional sextupole by the way, but also a higher order terms, including the canonical octupole. Importantly, the opposite is also true. When decomposing the kick from a conventional sextupole into Macmillan multiples, we find that it contains both a Macmillan sextupole and a Macmillan octupole. This explains why the detuning for this magnet is so non-trivial. As we see here, the conventional sextupole is not a pure quadratic nonlinearity. The Macmillan sextupole is. We know it from the form of invariant and solutions to the equations of motion. The conventional sextupole is a kind of Frankenstein we assembled in the lab, combining various pieces of nonlinearity. In fact, the detuning arises from the competition between two pure nonlinearities with opposite signs. To summarize, for a general thin lens, including for example a thin RF cavity when considering longitudinal dynamics, the detuning is once again determined by the additive contributions of two components, with the Macmillan sextupole strengths appearing squared. Notice how in this framework the overall picture remains qualitatively similar to the case of distributed nonlinearities. Although the exact detuning expressions for Macmillan multiples might still look somewhat complicated, their graphs are monotonic functions with singularities only at integer and half-integer tunes. Each function crosses 0 exactly once, at the tune corresponding to its intrinsic resonance, the third integer for the Macmillan sextupole and the quarter integer for the Macmillan octupoles. To learn more about intrinsic resonances, their degeneracy, the universal model of thin nonlinear lenses, and the generalization of these ideas to round beams and electron lenses, you are warmly encouraged to explore the list of articles provided at the end. Before we finish this part of this tutorial, we should mention one more important consequence. While Macmillan multiples provide an exact expression for the detuning, they can also serve as valuable approximations beyond the infinitesimal regime. As we will see, these model lenses can provide remarkably accurate approximations for lattices with generic thin lens, even those that allow chaotic dynamics, and stay invalid up to large amplitudes near the stability boundary. especially near resonances that are critical in accelerator physics. Because they allow fully analytical solutions, including explicit action angle variables and rotation numbers, they yield analytical approximations for quantities such as the nonlinear Betatron tune and the nonlinear emittance, which, up to a constant factor, equals to a nonlinear action variable. Moreover, the familiar sine and cosine functions used in the current Snyder formalism are naturally replaced by their nonlinear counterparts, the Jacobi elliptic functions. It is interesting to see how integrable systems still find their place in describing the real world, despite the presence of chaos, noise, and other yet undiscovered forces of nature. Just as Kepler and Newton captured the essence of Earth's orbit without knowing the true complexity of the solar system, which is in reality an n-body problem with n extremely large, Macmillan, who discovered his mappings to guide design and ensure predictable particle motion, ended up providing us with the best simple model for the nonlinear magnets he hoped to avoid. For the curious viewer, the second paper in the suggested list presents a complete solution to the nonlinear Kepler problem in discrete time, directly connected to axially symmetric lenses in accelerator design.